Richard joined. Internet is quite slow for some reason. Hello. Number 8. 831 757 6090. Guys in Zoom, can you hear me? Thanks, Richard. Okay, good morning everyone. Welcome to the Power System Production lecture again for this week. And before starting the day, do you have any specific questions that you want to ask me before going into the lecture? No? Okay. Guys on Zoom, can you see the slides? Unfortunately, I have to start with some problems here. Okay. Yep, thanks. What we discussed so far was setting up overcurrent relays. But before going into this, different type of other relays that we are going to discuss today, if you are interested in power systems, not only protections, but there's a very good report came out from AMO recently about why the market collapsed. Do you know that the AMO market has collapsed? Have you heard about what is AMO? So that's the Australian Energy Market Operator, right? So what they do is that they regulate the market and then defining the prices of electricity and then controls the frequency. A lot of activities they do. As utilities, and every utility has to send all these protection information and everything to them. But recently, usually the, say, generators, they bid for electricity price, but that market has collapsed due to certain reasons. And initially there were a lot of media discussions. Usually media is biased on one direction, saying a lot of things saying that our generators are wrong and all those things. But there's a detailed report from AMO. You can read it if you are interested, just to get some understanding about what has happened, right? So I would say that it's a very good report to read. If you are interested, just let me know. I think I have the link. Probably I'll post it in Blackboard, right? So you go there and then read it. It's not 100% related to protection, but it would be good as a power systems engineer to read that. Okay, so starting with that, what we discussed so far is a type of relay which is called overcurrent relay. But when you are going through these protection schemes, you will find that the overcurrent relay is not the only type of relay that exists in this world, right? And then why you need different other type of relays? Because the overcurrent relays have some sort of their inherent issues. So we will go through those problems one by one. It's always easier to explain something with an example. Assume that there is a sort of a fault at this point, fault at point X, right? And then for that sort of fault, that what I need is that I want to operate the relay at B13 and B31 and then disconnect this line, okay, as fast as possible. Say that I set this B31 relay to work as fast as possible, but then what about B32? Because the power flows through this and then going to this fault, right? The overcurrent is passing through B32 as well. It's a huge amount of overcurrent coming through this line. Therefore, B32 could be operated for this fault, which is not required. So what we need to do is that we need to slow down B32. Okay, we want to slow down B32. But now, what happens if there is a fault at Y? For this sort of fault, B32 has to be act fast, B31 has to be slow. So can you see that sort of a contradict situation there? B31 in one case has to be faster than B32, in the other one B32 has to be faster than B31. So that's why that the simple overcurrent relay is not does not satisfy the condition for a sort of a complex network where you have the loops. You can see that it's sort of a mesh or loop is there. It's not a radial system. In a radial system, it works because you don't have any connections back to the system again, right? But when you are going with this sort of system, we need to address those issues. So this is what it is. When you read the slides, everything is written here, what I explained so far. Okay, so what it says basically, because of this time difference between B31 and B32, they are not always satisfying the conditions for a fault at X and Y. It can satisfy the conditions for a fault at X or fault Y. Okay. So we need other type of relays for fault protections, right? So simple change for overcurrent relay is called as a directional relay, right? So directional relay is basically looking at the direction of the fault, right? In the previous one, it's whether the fault is occurred in, let's say, left-hand side of the relay location or right-hand of the location, the relay doesn't know. It will just look at the magnitude and then operate. But when you put the directional element, what is actually a directional element? Especially when you have these multiple sources, right? As an example, this is a simple example with two sources, right? So in this sort of scenario, let's say if the fault is at P1, right? And then you can see that the fault current coming from generator B is coming through this direction from right to left, and then the fault from A is coming from left to right, right? So for this fault, what I need is I want to operate only this circuit breaker and this breaker, which are marked in green. But if I have an overcurrent relay, you can see that this guy will also operate because he also can see the same magnitude of fault current is going through. Now, what we can do, we can set this relay to look after the faults in front of it. What I meant in front of it here is that from the bus towards the line, so that this guy will only operate for a fault in front of it, not any faults behind it. And then if I set the same thing for this relay, I will introduce extra element called directional element, which will look at only the faults in front of you, right? How we can do it, we will discuss, right? So what happens here, the guy with the red, he won't operate for a fault at P1 because it's behind him, right? But if the fault is at P2, it is in front of him, right? But there is a sort of issue here. You can see that the fault at P1 is in front of this green one as well as the red one after P2, because this guy is looking after any fault in front of it, right? So that for this relay, the fault P2, the relay can see it, relay at D, and then the relay at P, the green one, that can also see, that cannot see P2, but that can see P1. But this relay at D can see both P2 and P1. Can you see that? Because this relay looks after any fault in front of it. So P2 and P1, both of them are in front of it. Okay? So how do we resolve that issue? So we need to have some coordination between this green one and the red one at T. You need to have some coordination between them. But you don't have to have any coordination between these two red ones and then this red one and this green one. But of course, the green one at C and then the red one at P, they should be coordinated because they are looking at the same direction. So what we can do, once you introduce that sort of directional feature, then you will only look at in front of you, but any relay behind you which is looking at the same direction as the relay, the first relay, then you need to coordinate them. So that which relays have to be coordinated here? Let's say if I am looking at this set of relays, let's say 1, 2, 3, 4, 5, 6, 7, 8. So 1, 3, 5, 7 should be coordinated. It's like two, 4, 6, 8 should be coordinated, right? So because then those 4 relays forms a very similar network that we have seen before, like unidirectional. That's what we did in the previous examples. The couple of relays, overcurrent relays, which are looking after the faults in a certain feeder. So it is the same thing here, right? But there is no coordination between these two sets. They are independent sets. how we made it like that? We introduce a directional feature, right? So that we are looking at a certain direction. So how are we going to implement it? Mathematically, this can be explained in this way. Say, this is the current measurement system of the relay. This is the voltage measurement of this relay. So this current, you can see that if the fault is at P2, we assume that the current is going through this same winding. The direction of the winding is not going to be changed. It's the same way, always. It's fixed. So let's say for a fault P2, we assume that the current is flowing in the direction which is marked here. Now, for that current, this whole line is inductive. Therefore, we can assume that, okay, this current is lagging this voltage by certain angle, right? So let's say assume that this is the voltage and then the current is like that. Now, for P1, 2, we say that we have I2. This is I1. There's a current I2. That current flows in this direction, right? But your winding still the same CT winding here. You don't change it. So what will be the direction of this I2 if you assume that still the line is inductive? What will be the direction of the current in this plot? Let's say this is I1. Based on your phasor knowledge, right? Which direction what is the direction of the I2? Pardon? Second, here. The first, second, here. Yes, it should be 180 degrees. This one should be 180 degrees. It's reversed. Basically, reversed in phasor notation is changing the direction or angle by 180 degrees. So, what happens is that now, if you have a, say, some element inside which detects this angle and then decide, okay, if the angle is in this quadrant, first and fourth quadrants, then you will operate because you are looking at this direction of the relay. Let's say this is the forward direction, right? And then if the fault is in the backward direction, it won't operate because the current is in third or fourth, second or third quadrants. You got it? Yeah? This is 1, 2, 3, 4, and then forward current is in first or fourth quadrants. Backwards, it is in second and third quadrants, right? So what we do, we try to, this is very easy with the numerical relays, right? With the numerical relays, you just do the calculation and find the angle and then introduce that logic into the operation. Because the voltage, it will be the same. Whether the fault is here or here, yes, of course, there will be the voltage will be dropped, but usually just before the fault, the voltage will be the same here, right? And then while the fault happens, then we know that, okay, the fault is, current is in this side or the other side. Usually, identifying this voltage, it's a tricky bit for protection systems, because when there is a fault, especially if the fault is very close to the measuring location, then sometimes this voltage is almost how much? Zero, right? So can you do the measurement of a zero? What is the definition of zero? There's no definition, right? Zero is a very small value. So which means that when the voltage goes down, and then you have the limitations of your instrumentation as well, right? So you can't measure, let's say, I can measure probably 1 volt, but I can't measure 0.25 volt, right? There's a limitation. So for those things, I will come to that, those questions. Then you will have some techniques. Like as an example, you just take the voltage just before the fault, so that there is a memory in the system, and then it will take the voltage just before the fault, which is fine, which is the line voltage, right? And then when the fault occurred, if the voltage dropped to zero, then it can identify using that information where the voltage previously was, and then use that information to calculate these directional features. So there are sort of different techniques for those, right? So those things will be discussed in like in a different lecture, which how to address these issues. Okay. Now, so as I said, voltage reference, we defined it as Vt equals 0, and then the line is inductive. Therefore, the voltage divided by the mainly R is 0, right? You can, yes. So R is very small. So then this is close to 90 degrees. It's not 90 degrees, but close to 90 degrees. Right? So as I said here, for those two faults, we can write for fault at P2, I is lagging. For P1, I is leading. Looks like that. That is the extreme. Those are the extreme cases. Those are the extreme cases, right? So sometimes this could be somewhere here, and then this could be somewhere here, right? In reality. Right? This is what I refer to those dots. So by looking at these lagging angles, then we can easily identify the direction of the current flow. So what we do, we introduce some sort of characteristics to the relays, which will block the tripping for faults at P1, which is basically the backwards behind the relay. And then for P2, we say that introduce the trip for faults in this side. So how do we do that? We have to look at the relay characteristics. So what we do, you can see here, see, when you are dealing with these sort of characteristics, you can introduce this block line, right? The one that I mentioned before was basically the block line was here, but I slightly slanted it here. If you put the block line like that, then this region is trip and this region is block, right? That was the one that I have given here. 90 degrees, perfect scenario. But in reality, as I said, what you do, you need to consider, let's say, whenever you have three-phase faults, whenever you have line-to-line faults, these phase angles are slightly different, right? Because line-to-line fault, if you look at here, in the other one, depends on not this voltage, the phase voltage. It depends on voltage of AB, if the fault is between A and B. So line AB voltage is, the phase of it is different from the phase voltage. Line voltage is 30 degrees lagging there. So therefore, when you set this line, if you set it in the ideal way, sometimes you can't cover both phase voltage, the three phase faults and line faults. So if you want to cover both of them, you have to put these sort of different configurations. So that's what it is explained here, right? What we have to do is that we have to introduce this block line in such a way that during the every type of fault, the fault current resides in this trip zone. So that angle, that defines which currents that you allow or which currents that you will detect. Because if the current magnitude is large, and then if the current magnitude is large and then the current phasor is in this zone, the relay won't do anything, right? It's an extra element which looks at, like let's say you have an AND circuit, right? In one, if you satisfy both conditions, then it will send the trip signal to the circuit breaker. If it is only one condition, then it will just leave it aside. Like as an example, current magnitude is very high, but your phase angle or the current resides in this part of the circuit, right? Then what? It won't take any action. Just ignore it. So that is sort of a end condition. So it's like overcurrent and direction, right? So then trip signal, right? If both of them are satisfied, then it goes to the trip signal. So if one of them is there, then just ignore it. But setting up the characteristics, it depends on what is your requirement, what sort of impedances, magnitudes that you are looking at, angles you are looking at, right? So in this particular case, if you set it your, let's say, block line 30 degrees lagging the phase voltage, these sort of settings will help to cover both three-phase and line-to-line faults. Okay, the reason is that we know that VAB is 30 degrees lagging, right? Line voltage is 30 degrees lagging the phase voltage, right? That's what we discussed, I think, first class. And if it is lagging, then the fault current is perpendicular to that, same as here, right? Voltage and then the fault current is perpendicular, assuming that system is inductive, right? So you can see that this is the fault AB current. Now, typical AC current, then not only that, you need to look at AB and AC as well, right? Because when you are looking at fault currents, you have three different fault currents, line-to-line fault currents, A to B, A to C, and B to C. Now you can see that I'm measuring at A phase, I can configure fault A to B. Now I can configure fault A to C, right? Because this is the direction of fault AC. But you can see that BC is in the do not operation region. BC is in the do not operation. Why? Why we just push it into that direction? What could? No idea. Where was the relay? Because you have three phases. Where was the relay? Relay was in this particular case. Do you think in which phase that I have mounted the relay? You have A. Why? Because this is A to B, this is A to C. So that any fault current going through A, I identified it, and then I try to recognize whether that is in the trip region or not. But B to C, I can't measure it, right? Because my relay is in A. So that I need another 2 relays for B and C for other things, right? So when you are going with 3-phase system, you need to have relays for each and every phase, right? You need to do those measurements separately. It could be one relay where you feed all 3 currents, that's fine, right? But you need something which, or some way of measuring the all currents, all 3 currents, okay? So now, by looking at the currents in the relay A, then you can decide whether the fault current magnitudes are high, right? If the current magnitudes are high, and then also we know that my block line here is drawn in such a way that it can cover AC and AB. Assume that you put it here, block line, like considering only the A phase ones, right? Or in this case, I have, can you see that the difference between these 2 figures, right? When I jump from here to here, this is VAN. Now I change it 90 degrees rotation, see? When it comes to here, right? So that's why those 2 are slightly different. Can you see here? V is horizontal, real axis. Here I will write it, this is real. When you rotate it, this goes to imaginary, right? So that's the axis change, because just wanted to show you here, right, the voltage, and then the whole current is in the right hand side of that. That's all, right? So if you want to draw the same thing for this one, try to draw voltage in the horizontal axis, and then the current imaginary is the normal, real and imaginary axes, and then try to construct this, right? So just for your understanding, okay? So it is the same thing, these 2 are the same thing from the voltage point of view, but the difference between these 2 is here my block line, let's say, if I want, in the ideal case, it is along the voltage axis. This is also along the voltage axis. But I have shifted 30 degrees from here. If you take that 30 degrees here, then those 2 are identical. Okay? So if I take 30 degrees leading, then the left hand figure and the right hand figure are identical. So what you need to understand is that you need to, like ideal case, it is along the blocking line is along this voltage axis, but we are not going ahead with that, because one of the major reasons is that you want to cover both 3-phase and line-to-line phase. So if you want to cover both, then you have to introduce this sort of lagging, right? So these are usually coming with relays, these sort of settings. You don't have to specifically introduce. They will give you some instructions how to cover it for the 3-phase and then line to line, right? But you need to understand this concept, right? So if you get a relay and then if you want to program it, probably you have to put these all information there, right? So which direction that it covers. Okay. Have you guys discussed this in the class, tutorial class? Right? I think I already asked him to discuss just to get some understanding about directional relays before I start teaching about it. So was it clear, or do you want me to go through this? This is quite the same, like which breakers will not operate for a fault at P1? Can you tell me which breakers will not operate, right, will not operate for a fault at P1? Can you tell me which ones? Fault is here. which ones should not operate based on directional features, which one should not operate. There are B, B2, B21 should not or should operate. I'm asking should not, will not, breakers which will not operate. 2, 3, yes. 2, 3, 4, yeah. And then what about B4? B4 is looking after, usually B4 and B1. Okay, which one of them should be directional and which one of them should be non-directional?
Only the one between buses.
Pardon?
Only the one in between buses are directional.
Yeah, these are directionals. So if you think about all these ones, they are directional. Why this one and this one, they are not directional?
Because there's only one.
Pardon? Why they are non-directional?
They're beside a generator.
Yeah. When there is something next to the generator, what happens if there's a fault inside the generator somewhere in between the brake and the generator, right? So let's say if I put this one as directional, only looking at in front of it, right? So if there is some sort of a fault here, because of this generator, huge current is coming through that, and then this generator, there should be something like to protect this generator as well, internally certain things, right? But then this fault, that if there is a fault here, this breaker should detect in both directions, because it's a generator protection, it's not a line protection there, right? So it's usually they are non-directional. But then if it is in between buses, usually they are directional, right? Yeah, so even for the P2 and P3, you can find similar way which breakers should operate and then which breakers should not operate, right? For a fault at P1, then breaker B21, B32 and B43 should be coordinated, right? They should be coordinated. That's what I said in the previous slide as well. So always, if breakers are, or the relays are capable of identifying the faults, then those relays should be coordinated. That's all. Okay? Now, when you put these directional relays for these sort of multi-loop systems, it is always very, very hard to determine which one is which, right? You can see that, okay, for a fault here, these two are looking at those faults, and then sometimes this one is looking at the same fault, right? And then this R2 is looking at the same fault, right? So R1 is also again looking at the same fault, right? There are many, many relays, right? It's not 2 or 3. And then many different combinations are there, right? Large number of combinations are there. So it is very, very hard to, it's a very complex system which sometimes that your manual calculations doesn't work if you have too many these sort of loops, right? Identifying which relays should be coordinated, and then how do we set those coordinations, it's a bit hard. So usually the process is that you try to identify the minimum number of relays which could isolate the whole system and then coordinate between them. Minimum number of relays which could together break all loops here. Can you suggest minimum number of relays required to break all these loops? say you have three, let's say how many loops are here? Or how many meshes are here? 3. 1, 2, and then the big one. You have 3, right? To break all 3, how many relays should be operated? Like, for a fault you can consider the faults at any location, okay? So if there's a fault, and then how many relays should operate to disconnect the complete system? You can consider a fault somewhere here, or here, or here, here, anywhere. For a fault, how many minimum number of relays should operate to completely disconnect the system? That's the question. This is, human can do this, right? But when you have, let's say 50 loops like that, definitely you can't do it. So then you need to go for some sort of a combinatorial optimization techniques, computer-based techniques. You may have to use those, but here you can. How many you think?
6.
6. Do you think that you need 6? Yes, I know that you are looking at this central part, right? Breaking all this, right? So 6 means if you break all these, then definitely the loop will be broken, right? If you open all these 6, then just definitely. But do you need 6? Isn't it too much? Good start. Is there anyone in Zoom? Can you suggest how many breakers should operate for any sort of faults if you want to completely disconnect the system, you know, the fault, completely isolation of the fault, minimum? Break all loops during a fault. 3. So why do you say 3?
This is only 3.
Yeah, only 3 meshes, that's one way. But then also that physically you can see here, let's say if you have a fault here, right? You need to break this guy, right? But then the fault is feeding from here, right? You need to break that one. Now the fault is feeding through this guy, right? So you need to break this one as well. So you can see that if you break all these 3, right, this fault will be cleared. That is the minimum requirement for that. Okay, but now if you're looking at any other point, right, any other point, you can see that you need only 2, right, just in between them, right? But here, how many you need? For this fault, again 3, because these 3, right? So that is the minimum requirement for this whole system to operate, right? So with 2, you can control it in between these feeders or any transmission line. You can disconnect using 2. But when it becomes one of the buses, you need at least 3 here. So that is the minimum breaker number which could operate together to break all loops, right? And then once you identify that, you can come up with minimum assumptions on relay settings for all coordination systems. So once you identify that, okay, I need 3. You need to coordinate those 3 now, right? So those are the fastest operation there, because if those 3 has to be break for a fault somewhere here, right? And then after that, you need, once you set those times for those 6 relays, then you can coordinate the other ones with that. So that's the only way for this sort of system. But when you are dealing with, let's say, very high complex systems, then it's really hard to do it manually like here. Now we can see those things here, right? We can like, our brain can visualize it, right? But when the system is so complex, you need some computers to use some optimization, right? So that is what they do for these sort of loop systems. So the loop system, yes, directional relays are possible, but you need to do some more computational analysis. So some limitations of these overcurrent relays, they are less accurate. Why I said less accurate? Because it's just a current measurement, right? And then you need to have some boundaries between the overloading conditions and then short circuit currents. So it's always, accuracy is a big issue, right? Overcurrent relays are not that accurate. And then they are not suitable for complex mesh transmission systems, right? And then because selectivity and sensitivity requirement are very, very important for those sort of systems. What is selectivity there? Selectivity is there for a fault. You want to identify which part of the network has to be isolated. You can't do it with the simple overcurrent relays. Then everything will be isolated, right? And then the systems are looking for very sensitive operations, like, you know, if there's a, because if one line is, you know, disconnected, whole system go into blackout, right? So that is a very complex system, right? So then, therefore, if you just put the overcurrent relays, then they will probably disconnect a couple of lines, right? Instead of one single line. So then it's not sensitive enough. And then also, which is important, is that when the fault current is comparable to the load current, what does that mean? Let's say sometimes your very high impedance fault currents, they are not very high. They are sometimes very close to the load current magnitudes. Then when you define the current, fault currents, that there should be some sort of a margin from the load current to the fault current. And then you can't detect those small magnitude of fault currents using this technique. So because of all those issues, we introduce another technique called distance protection. So distance protection, in the overcurrent protection, we had only one element of measurement. What did we measure? In the overcurrent relays, we measured path current. But now what we are going to do? We are going to do two measurements, introduce. So once you introduce both measurements, what is the other measurement that you can do? Voltage. So now what we are going to do, introduce a technique where that you are looking at both measurements. So once you have the voltage and current measurements, then you can measure the impedance, something called impedance, voltage divided by current, right? So if we have a relay, as shown here, right, fed with the voltage and current measurements, Then the relay will calculate the impedance. Impedance is basically the voltage divided by current. And then, depending on the value of this impedance, we will define whether it is a fault or a normal condition, depending on this impedance. So that is what you called as basically distance protection. That is the fundamental behind it. Very easy, right? So now, the most important part is that how do you define that boundary? Based on what? Right? So like overcurrent relays, it was really easy. How did we define? Our pickup current is defined based on the fault current magnitudes, right? Now we need to find a way how we can define these boundaries. So that is the most interesting part for us, right? So engineers, they have to design in a way that the proper boundaries for this impedance. So once you define that boundaries, the operation is simple. If you are inside the boundary, then you say that, yeah, it's a fault. If you are outside the boundary, then you can say that, no, not within the operation region, right? So we will look at it in detail. So during a fault, what happens usually? The voltage drops, current increase. Then what happens to the impedance? What is impedance? Voltage divided by current, which means that definitely impedance should go down. Impedance should be dropped. So then which means that we have to define a circle or define something to define the impedance. Within that boundary, you can define it as a fault. Beyond that boundary, we can say that it's normal condition. So that's how the fundamental concept comes. So we are providing the CTs, using CT's current, using the potential transformers, we are giving voltage to the relay, right? So as I said, if the impedance is less than a certain impedance value, then strips, else block. So always remember that when you are dealing with the relay concepts, block means that relay is not operating. Trip means that send the trip signal. So that is the sign, the language convention there. Okay? Okay, now we'll look at how we can form it. This small explanation gives you how do we define loading and fault conditions. Say under the certain load, let's say this is 132 kV 300 MVA system, just for your calculation purposes. Now we have a certain voltage here, phase voltage, which is 132 kV divided by square root 3, right? System voltage. And then I phi is S divided by square root 3 VL. That is the phase current, right? Or line current. They are the same here, right? In one line, that is the current, right? So if you want to find the current, in the total power divided by square root 3 VL. So that's what I found. The current is 1.382 kiloamps. Now look at, because say when you are looking at a relay is doing, always measuring impedance, always looking at the voltage, looking at the current, divide these two, and then looking at that value. Continuously, it's doing that. So now I have a relay here. This guy is measuring the phase voltage and phase current continuously. Now this is the maximum load that I am, let's say, supplying by this line. So this is the maximum current that I am sending through this line. So that is what is the impedance of the line then. Impedance that you measured here. So that impedance is the voltage divided by phase current. Voltage is here, 132 divided by square root 3, 1.382 is the current. Impedance is 58.1 ohms, right? So that is the impedance seen by that relay. When supplying the full load. What happens to this impedance when I am supplying a load lower than this? Now look at those set of equations which I use. If I reduce the supply, because I don't supply the maximum load all the time, let's say now I am supplying 100.
Increases.
Yes, why it is increased? Because when S is dropped, I drops. When S is dropped, I is dropped. If I is dropped, then Z is increased. So which means that this is the minimum load impedance that you can see. It could be above that, that's fine. So that is the condition for loading. Now let's say there's a fault here, somewhere in front of you, right? So the fault current is IF. Impedance of the line from this point, or the relay point to the measuring point, the relay measuring point to the fault location is ZL. Now what we measure as the fault impedance, again relay doesn't know, right? Relay doesn't know whether there is a fault or load or whatever. What it does is that it just measures the voltage and current. So voltage and current measured V phi divided by I phi. V phase is divided by what is the current this time? Fault current. But also the voltage here this time is line impedance or total fault impedance. Put it in that way. In this case that I thought that okay, there is no fault impedance. It is just the line impedance. ZL times IF gives you the voltage there. This divided by this, finally it is the line impedance. So what relays now see, relay sees the line impedance. It doesn't see the load impedance now. Because of the fault, instead of that, what it can see is the line impedance or the impedance in front of you. Okay, now what is the typical line impedance? Is it 58, 59 ohms, something like that, or is it always 0.1, 0.2 ohms, something like that? Line impedance changes with what? Length of the line, right? Because this fault can occur any point on this line. So usually impedance of these transmission lines, if you are looking at, very, very low. If you have very high impedance, then definitely there will be a lot of losses in the lines. Voltage drops in the lines, right? So you design it in a way that you will have very low impedance. So therefore, ZL is typically very low. I can't give you an exact value here because the line impedance changes based on the type of the lines, tower design, a lot of things, right? But they are very low. Always they are low. So, and then of course the temperature, right? When the temperature changes, line impedances slightly change, but they are still low. So, since the line impedance is much smaller than the load impedance, then we can detect those faults using this technique. So once you have those measurements, then you can detect. So that's the way the impedance relays work. So that what we do, okay, now we know that my operating region should be less than 58.1, but if you know the line, the longest length or the line that you are going to protect, then that value should be the cutoff margin. Like you are not going to detect anything beyond that, but below that line length I can detect anything. So that is quite an easy way of doing it. Now when you are looking at it, impedance, if you are plotting this in R and X frame, impedance is now what we said was just a magnitude, right? So if you want to look at a magnitude in the RX plane, single magnitude, without thinking about the phase angle or anything, what should be the characteristics? It's a R vector, you have only a magnitude, any angle. So it's a circle, right? Because you have a magnitude, any angle. So if you look at characteristics, it looks like that. See, any impedance beyond ZR, it blocks. Less than that, it trips. Got it? So that is called impedance relay. So in an impedance relay, that you will just have magnitude of the Z. Beyond that certain impedance ZR, the relay will block. Below that, the relay will trip. So that is the condition. So always you measure that impedance and then finally take the decision. Understood? Clear? Yes. I can give you 2-3 minutes break if you want. Yeah. Guys in Zoom, do you have any questions? Okay, so let's start it. And regarding the impedance relays, as I said, the Z is equal to R plus JX always. That is the line impedance. Therefore, the relay operating region is a sort of a circle, right? Because JX can be any direction here, right? In forward direction or backward direction. So that this sort of relay, they don't have the capability, the directional capabilities. It's non-directional relay, because you look at the folds in any point under any loading conditions, right? Typically, it could be somewhere here, or if you are looking at the reverse direction, then probably somewhere here, right? So, but there's no directional feature here. And under normal operating conditions, as I said, Z should be larger than ZR, and then for a fault, less than ZR. So impedance will move into normal operating conditions. Impedance will be somewhere here, and then once the fault occurs, then the impedance suddenly jumps into inside this region, because you are always measuring the impedance, right? It's continuous measurement, and then when the load is, you know, like when the supply is supplying a load, then the impedance is somewhere outside, right? Depending on the type of load, depending on the direction of the load, then this operating point for the loading conditions could be somewhere in any of these four quadrants, right? Doesn't matter, because there is no directional feature here. So that's these sort of characteristics. Circle. The origin point is you can say that this is the point of the relay. From the point of the relay, you measure the impedance, right? So therefore, origin represents the point of the relay. From that point, what is the magnitude of the impedance of the line if you go along this ZR vector? It could be somewhere here or anywhere from center to outside along any radius, right? So that will give you some sort of impedance. So that's how the relay basically works. But if you think about the real operations, if you want to look at only the certain direction, right? If you want to look at only a certain direction, then operation of this relay should restrict into one quadrant. Let's say if I restrict it into first quadrant, then I can make it as a relay which only looks at the forward direction. So that's the next part of it, is that we will first look at why the directional feature is required for these sort of relays, and then we will look at how we can introduce the directional feature for these relays, right? So why directional feature is required, if you look at this diagram, then I can explain it very easily. Say you have a fault somewhere at P1, okay? For a P1, yes, definitely B12 should operate very fast, and then it will operate, right? B12 will operate because the impedance, I will set the impedance of this relay, operating impedance of this relay, to a very large value, right? Forget about the zone and all those things, right? There we will discuss them later. But for this description, what I need is that focus on the fault at this P1 location. And then B12 will identify that fault. And then B1 will take some actions, and then this line will be disconnected. That's fine. Now look at a fault at P3. Okay? Let's say the impedance from B1 to P1 and B13 to P3, they are the same. Let's say the impedance of the line, in both cases, they are the same. Now for P3, what happened to B12? What is the impedance? It's like impedance seen by B12. What is the impedance seen by B12? Is it equal to the impedance of fault 1 or not? Say now in the first case, IF1, and then let's say Z B12, 2 for IF1 is equal to, let's say, Z1, right? Then second, this is fault 1, this is fault 2. For a fault 2, ZB12 IF2 is equal to Z2. What do you think about Z1 and Z2? Let's say this, right? Let's say impedance of line from here to here is Z. This line is also Z. Forget about B13. I'm asking about B12. Now B12 has to see that. Very similar. Why? Because you can see that B12 is connected to this bus. And then in this case the fault current is going through here. In this case it's coming through somewhere else, and then, you know, very similar to this. Because this guy will see a fault current and then, right? So because the fault current, you can see that, see, fault current is coming through this path as well, right? And then in this case it's going through this here from this generator, but in this case it's going from this generator through this one, right? Because at the end of the day what you are looking at is the impedance, voltage divided by the current, right? So this generator, this B12, Z1 and Z2, both cases equal to Z. Now the problem is, which means, let's say I set this relay to operate at a certain value. For P1, yes, definitely it will operate, that's good. But now for P3, B13 will operate and also B12 will operate now. Is it good? No, because I don't want to disconnect this line for a fault on B13 line, this line. So that's why the difference between these two scenarios is, one, the two faults occur in two different zones of that RS plane, right? For fault P1, it occurred in the first quadrant, but this one occurred in probably second quadrant or third. So now you can see the difference between those two. So that's why that we need to, like, if we just go ahead without any directional feature, then still we can't protect or we can't increase the selectivity. There's no selectivity there. So the relays will operate for unnecessary faults. So that's why that we need to introduce some sort of directional feature. So how we introduce those directional features we will look at. So this is the same explanation, right? If you are reading the slides, that information is there, which I explained just now. That is the explanation given what I explained so far, right, using this figure. So what we do, we introduce a directional feature where you can look at, say, the trip, it will trip only in the certain region of this RX plane. One way of doing this is that you introduce a extra element, like in the previous case, you can introduce an extra element, which is the directional element, which will look at only a certain direction, not on the other directions. That is easy. But then there is another way of doing it. If you are looking at the characteristics, you shift the characteristic curve, right, in such a way that earlier your center was here, right? The center point was here. Now my center, I shifted it towards the first quadrant of RX plane. So now earlier circle was this. Now I shifted it to here. Right? You push the characteristic curves. You can do it mathematically as well. Right? So there are enough maths to shift a curve from one location to another location. So what we do, if you shift it like that, Then what does that mean? Now still, can you shift your measuring point? Measuring point is the same, right? We just measure something at a certain point. So still, what we do, this is the measuring point. We set this vector up to here is the maximum length that you want to cover. This is the impedance, right? Line impedance. So let's say if your line impedance is 10 ohms, that is the 10 ohms that you want to cover, then this distance from origin to that point should be 10 ohm. So that we created a curve or the circle, but that circle has been now shifted, right? So once you do that, now you can see that your fault is somewhere here for P1, but P3 now is somewhere here, right? In the previous diagram, if you look at here, P1 and then the P3 here, right? Got it? So if you look at here, now once curve is shifted, still the P3 is here. You can't shift the P3. That is what the relay is doing the measurements, right? So P3 is here, but the curve is now here. Therefore, it doesn't know what's going on at P3. Basically, I don't care, right? So now only the faults in this zone will be identified. Anything outside that is not going to be. So that's the block region. So now you introduce some sort of a directional feature without introducing any additional extra elements. So that is why that sort of relay is called as Moore relay, the reverse of Ohm. Okay, so it is because you can define or derive this using, if you look at it in the admittance plane, it's sort of a line, it's a sort of a line. So that's why that they define it. Now, because now we are looking at everything in the impedance plane. So you call it as modified impedance relay, or you also call it as Moore relay, right? Not Ohm, it's Moore. Okay, so that is how they defined it. So as I said, it's a simple modification. You shifted it, origin is here, but this length is the line length, right? And then when there is a certain impedance that it measured, what it does, it calculates the distance to that point from the center of this circle. Got my point? The distance to the impedance point from the center of this circle. You can do that calculation using any numerical relay very easily, right? How we do that? Let's say here the distance to the center from the origin is Z dash. Z dash is basically ZR divided by 2. ZR is usually the line length which you set as the operating point of this, like the zone defined by this relay. Like as an example, if the zone looks at let's say 100 kilometers of the line, then you have to find the impedance for that 100 kilometers, then that is equal to this ZR, right? So ZR is, I will say, impedance of the line, impedance of the line protected by the relay. Okay, that is ZR. Now once you find that, then the the center of the relay, or the center of this circle is a dash, the distance is a dash, which is equal to typically ZR divided by 2. right? So if we know that is a dash, right, then if we want to find there is a certain impedance here, right, impedance of Z, it is the measured, this one is the one measured by the relay. So the relay at certain time interval, it just measured something, right? That is the impedance Z. So then we can find what is the this vector. That vector is basically Z minus Z dash. Do you get it? That vector is Z minus Z dash, because this vector is from center to here minus Z plus Z, minus Z dash plus Z, the vector. Did you get it? That is the magnitude of this one. Got it? No? Vectors, there are 3 vectors. I'm looking at. This is Z dash, this is Z, therefore this vector is Z minus Z dash. Do you agree? Okay. So now that is Z minus Z dash. If that is the radius, that is the length from the center, sorry, that is length from the center. If this vector is larger than the radius, if that vector is larger than the radius of the circle, are we in the block region or trip region? Pardon? Block region. Because larger than the radius, we are outside. So if this is radius is Z dash or ZR, divide by 2. Right? If it is less than, this is block. Block. And then if Z minus Z dash magnitude is less than ZR2, then it is a trip. That's what it is written here. Right? I took the 2 to the other side, right? So that you have this condition. So once you find that, you know, mathematically you can find all these things, right? Very easily. And then once you then find these values, then you can identify whether the line is going to be tripped or line will be plugged. Right? It's quite easy. And then the good thing with this one is that it will only operate in this region. Right? If the impedance is backward somewhere, you don't look at it. So the directional feature is given for the impedance relay. So it is quite straightforward. You don't need any extra elements. Using these characteristics, you can provide the directional feature. So as I said, that Z dash introduced the directional component, the shift in the curve. Yeah, as I said, if impedance is in the 3rd quadrant, then that will be definitely avoid tripping. Not only this, when you are dealing with the new relays, you don't have to just look at that circle. Why? Numerically, in numerical relays, using mathematical expressions, or you can use, even you can define those graphically certain ranges. And then the relay knows that whether I need to, what is the boundary. It doesn't have to be just a circle. So that will help us to, let's say, improve the accuracy of these relays and then improve the reliability, right? So if you are looking at the modern relays, then you will have these strange character, like the same impedance plane, but instead of that circle, you can find these very different characteristics. Why you need them? Because certain lines have their own sort of specific features. To address those specific features, sometimes you need to change the shape of these characteristics. Like as an example, very good one, this one. This introduced very lengthy R value, right? Usually, typically it's a circle. The R value is smaller. Now you can go for a very large R values here. What does that mean? Which means that if the arc resistance is high, still it can detect. If you have a line where that there is a potential for having a lot of arcs, right? But you want to detect them, then the arc resistance has to be detected. Otherwise, because of that arc resistance, if the impedance is large, then you are going away from that circle. To avoid that, you increase the R side without increasing the X side. So you can do that. And if you look at this one, this is strange, like it's called lentils characteristics, right? So because in this one, sometimes that you can accommodate extra loading because of, if you have this curve here, and then you, let's say, sometimes that you can, in a normal circle, sorry, not in this one, the extra one loading is this one, sorry, this one, right? Because if you are having a normal circle here, sometimes that when the extra loading comes, then those loadings will come into this circle. To avoid that, you change the characteristics in such a way that extra loading will not come into the characteristics. So because of other requirements, it's not protection requirement, but the system requirements, right? If the system is behaving in a different way, then you can introduce these different characteristics, put it in that way. So each of them have their specific features. Yeah, so this is a very good example of these, in this set of relays, how the load can come into the let's say, relay characteristics. If the load comes into the relay characteristics, we call it as load encroachment. There are ways people can introduce to avoid load encroachment. We call it as load blinders. What load blinder means, that the relay will be blind if the load comes into that blinder region. Relay is blind. Blind means that if the load comes into the relay characteristics, you define a blinder line. I will have one question based on that, right? I will discuss it using the question so that it will be more clear. But load blinder means that you define a sort of a blind line. If the relay characteristics comes into the load comes into the relay characteristics, because this is the relay characteristics. But if you are in this region, then the relay is not going to look at it. Oh yeah, that's something happened with the load, so I'm not going to look at it, right? So you have the full characteristics, but since you define this load blinder, then relay is not going to look at it anymore. So that's one way of simplifying the issue. Because one of the major issues with that, this sort of relays, is that when the load increases, impedance drops, and then impedance could come into your relay defined characteristics area, right? So you have to find a way of avoiding unnecessary tripping there. So one way is that introducing this. There are many other techniques, but this one is one technique. So why it happens? we can quickly explain it. We know that impedance is voltage squared divided by the S. Voltage squared divided by S. And then we can multiply both, denominator and numerator by Pi minus J minus plus J Qij. So this becomes this one times this, right? So then, let's say, I will erase this one. No, I can't erase that one, right? Okay. So this one, you can rewrite Vi squared divided by, this term is S. So S squared actually times, if I write, or if I take the square root of P Ij plus Qj, Jqij, then you can write this one as cos theta plus j sin theta form. Got it? This parameter is equal to S. Therefore, we can rewrite this. I think I should, somehow I can't delete what I have drawn here before. What I will do, I will change the ink color to, I will remove this so it will be much clearer for you. Okay, now I have enough space there. Is it raining outside?
No.
Oh, back again. Okay, so the same thing you can write Vi squared divided by S squared times S cos theta plus j sin theta. This says, which means that this is ZR. We can write ZR is Vi squared divided by S, that is the magnitude, angle theta. Right? So which means that the impedance, the relay impedance which you measured is proportional to, voltage is fixed but apparent power. So always the relay impedance, the magnitude that what you measured, is inversely proportional to apparent power. That is the magnitude of apparent power, right? Which means that when the apparent power goes up, impedance drops. So that's what you call it as the load encroachment, because when the apparent power goes up, then the impedance comes into this region, right? If you don't have, if you have, let's say, a very small circle, then probably you will be safe. But when the line is longer, or let's say instead of 200, if you want to look at 300 kilometers, or if you want to look at 500 kilometers, then the circle becomes larger, right? And also, I will come to that, with the impedance relays, you are not only looking at the line just in front of you. Sometimes that you are looking at further away. Why? You need backup protection in the systems. So sometimes that you are looking at not only just in front of you, you are looking at further away. So if you are looking at further in front of, like let's say further away, then what happens to the impedance? Impedance becomes larger. So once the impedance becomes larger, then the circle radius becomes larger. Once the radius becomes larger, then you are getting closer and closer to the load impedance. So if the load impedance is coming to the circle inside, because now If the power, apparent power goes up, then the impedance drops. So if you're coming into this circle here, then we call it as load encroachment. So we should avoid load encroachment for a proper operation. So there are techniques that people take to avoid that sort of things. The load blinder is one of those techniques. We will do one calculations with them later, then you will understand what that load blinder is. So as I said before, it's a very common practice with these impedance relays to look at different zones. Zones means that I'm looking at, let's say, in front of me as well as little bit further down. So zone 1 they define, that's how that they define the zones. First zone means that in this zone I'm looking at any folds within the defined zone 1. And then I set some sort of a operating speed for the relay, like instantaneous or 10 milliseconds. Any folds within this, the relay will operate in 10 milliseconds, put it in that way. Now, how do we define that zone? See, this relay B12 looks after everything up to B21. So the best is that my zone 1 should go from here to B21. But you can look at here, zone 1 is defined only 80% of this line, not 100% of this line. What could be the reason? Why I am not going to 100%? Now think as an engineer, not as a scientist. Why you don't want to go for 100%, but you just set it at 80%? Think from the angle that nothing is perfect.
There's going to be like some margin of error, and you don't want it to go past where that next one is.
Exactly. That's the engineering way of thinking, right? So you just have to think, okay, if I go 100%, then we don't know. When you set 100%, it might operate for 105, right? Boom. Then what happened? When the fault is in the next line, somewhere here, right? The zone 1 will operate. We don't want that. So the best is that, of course, there is a problem with that, because if you set it to 80%, which means that it won't operate for these faults very close to the other one, right? But you have to have some sort of a compromise, right? The compromise here is, okay, you set to 80%, right? So remember that what we are now discussing is basics, right? In the reality, it will go up to 100%. I will explain those things later, okay? So, but when you define the zone 1, still they define it like that, okay? But then there are ways to look after the faults here. They are different, okay? I will come to those things later under different schemes like pilot relays and all, right? But then in this scheme, you just look at only up to 80%. So that up to 80%, we call it as the primary protection of that relay. That relay will operate as fast as possible, not going up to 100% of that line, okay? Then zone 2. Then we define, okay, another zone, but that zone will operate with a little delay. Like in the previous one, it operates instantaneously. The next one, about 0.2 to 0.3 second delay. You are not operating, you are just waiting and then looking at, okay, what's going on. And then if still it's going on like that after 0.2 to 0.3 seconds, send the strip signal. Now, what is that zone? they define it as to 120% of the reach, which means that 120% of this line, which means that you are jumping next to the next line, or 100% of this line plus 50% of the shortest adjacent line. Shortest in what sense? Length? Shortest from the impedance point of view. Okay? Because impedance could be different for two different lines. Typically they are the same, but it could be different. So if you have two lines, like per kilometer impedance could be different for two lines. So what you need to look at is 50% of the shortest impedance of the adjacent line. So if you're looking at here, 50% of this line or 50% of this line, depending on which one is shortest, right? That is another way. So the zones or reach is defined in their standards and all, right? So we can't change those things. Those are the universal agreements. Okay? You can change it because you have the features to change it, but then these are the typical values people go for. Okay. Zone 2 relay provides backup protection for the other drones as well. Like, if B24 or B23 is not operating for a fault just in front of it, then B12 will operate so that you will get a backup protection. B24 and B23 are operating instantaneously for the faults just in front of them. And then if they are not operating, this guy will operate with a certain delay. Got it? Clear? Then introduce zone 3. Right? Believe me that I'm not going beyond that. Okay? Zone 3. Right? Not 4, 5, 6 like that. Okay? So zone 3, you define it. Relay reaches set to 100% of this line plus 120% of the either line 2 or 3, which is the longest here. 120% of the line 2 or 3, which means why it is longest here? Because you want to cover the next of this bus. Because if you go 120% of the next, which means that you are going beyond the next bus, right? So not this bus, but the next one. So if you take the longest, which means that you will cover this one and this one both. If you take the shortest, then it will cover one, but not the other. So if you want to cover both of them, then you need to go for the longest. So that's what they have done with the zone 3. But the zone 3, you can see that it's a very huge delay. 1 second delay means 1 second is huge for a transmission system, right? 20 milliseconds, 1 cycle. And then how many cycles are there in 1 second? Then 1000, right? 1000 milliseconds divided by 20. So it's like 50, right? 50 cycles. So you have 50 cycles. Anything could happen during that time. So this zone 3 is just as a backup protection. If something really goes wrong here, and then if none of these guys are working properly, then you need to take action just to avoid a lot of issues, right? So that is how they set this. And then once you have now 3 zones, then we need to have 3 circles, because we define now 3 zones. So that's sorry, I think it's not drawn here. I think it should be in another yeah, so here, like that, right? So you have zone 1, zone 2, zone 3. See, now when you go to the zone 3, one of the major issues is that your load could encroach into here. See, now very, very hard for the load to be encroached in this section, right? But there is a chance that load could be encroached into zone 3, because zone 3 is very large. The impedance could go closer to the load impedance. So that's why those load encroachment, the different approaches are there to avoid that. So And also, now, for these different, like let's say if you have a fault at P2, then B23 will operate. But if the B23 cannot operate, then B12 will operate. Now you can see that fault at P3, this guy will not operate. B12 is not going to operate now because it is not in his zone, any of the zones, because it's in the reverse side, right? It's in the third quadrant. So it's only this guy. And then you can see that zone 2 will look after any faults up to here, but if you have another relay here, it has its own primary zones, right? So that primary zone, if that is not operating, then B12 is operating as a backup, right? Even if there is an issue with this, let's say, transform area here, something on this bus, then B12 will operate, but with a huge delay. So that the advantage of this is that you don't need extra relays as backup protection. It's only one relay with 3 different characteristics, so that you can save cost or save the protection cost, right? That's another advantage. And then you are not introducing extra elements there, right? Large number of elements in the system. So if physical elements, if you introduce more and more, then the reliability goes down, right? So those are the advantages. If you plot the time distance characteristics for these relays, say with the impedance, let's say this is my X is the relay here, the operating time is instantaneous up to 80%, then suddenly the operating time increases to T2, which is roughly 20 to 30 milliseconds, right? And then you can see, in certain cases it could be not 20 to 30, sorry, it's 200 to 300 milliseconds. Did I say correct? Yeah, 200 to 300 milliseconds, 0.2 to 0.3 seconds, right? And then 1 second after is at 2x. Similarly, you can draw the same thing for this one, right? And then for the reverse relays, it is the other direction. The advantage of this diagram is that, see, you can see that if this is not operating for certain regions, let's say for certain case, if this is not operating up to this point, then this guy will operate. And then this guy could operate. The other advantage for this is that if for some reason my primary impedance element is not working, then still there is a guy, because he can see it, right? Like let's say if the fault is just in front of you, all 3 elements can see it, right? Because that impedance is less than Z1, less than Z2, less than Z3. So all 3 elements can see it. So itself is a backup, so that you have primary, you have secondary, and the third one, right? So that typically if one fails, then the other one can act, right? So those are the extra advantages of these sort of relays. Okay, so 49, I have to stop now. The rest is calculations, right? So we will do it on the first hour of Friday class, and then we'll go from there. And then I'll post the answers. I will post the recording. Recording is available for this week for tutorial. And the other thing is I have to mark the assessments. I will do that as well this week. Okay. There was another thing. Yeah. So I will upload the tutorial for this week as well, a new one, based on the impedance relays. Any questions related to the PSCAD labs? It's going well? Good? Yeah, it's good. So I think the relay knowledge that you requires for the PS CAD lab is done now, right? Because it is only the overcurrent. It's not based on impedance relays. So then now you can complete it if you want. Yeah. So any other questions? No. Okay, guys on Zoom, I'm going to stop here. Do you guys have any other questions? Yeah, so that will be, we will try to mark it this week, right? So, but even if I don't upload the marks, I will upload the answers. Okay, so but I will try to mark. Yeah.
He meant like when is the second one coming up?
Oh, okay. Oh, yeah. That's week.
It's due next Friday.
Due next week Friday, right?
Yeah.
So that it will be available this week then.
Oh, okay. Alright.
Yeah. So we'll give you minimum 1 week,
Okay. It's due in like 20 weeks.
as I could remember. Yes. So I'll upload it this week. Okay. Thanks. So.
I have one question.
Yeah.
So for PS CAD, like
Yeah.
the ICT, I noticed is only up until week 7, right? So that is for like the report writing for that PS CAD, right? And then after week 7, there's like the actual physical crack.
Yeah. And
that
then.
is completely different from the PS CAD, right? They're
No,
not
that's the relay testing.
right.
Yeah, but there will be a small section. When I upload those, probably you can read that in the PSCAT report.
Right.
There is a small section that you need to do with the. You need to fill from the.
From the crack.
From the crack.
physical crack.
Physical crack.
So like there's only one report that we actually submit this semester.
I'm not allowed to give you to submit to.
Okay. So like in this report, it will include both the physical, like the relay testing knowledge, and the ICT like simulation. Okay, thank you.
Because I think according to university rules, you can't have two something like that.
Oh,
There is some regulation now.
Right. Okay.
That's based on that I can only.
So then it will. So essentially, the due date for the report will then be like basically after everything that, even after like the physical process. Okay.
Due date is somewhere in
Near the week. The
12 or something, right?
Alright.
Because that's why that I had to push it.
All right. Okay.
Because I had to wait until all of you finish the lab. I can't say that our due date is, before the mid-semester, right? Previous year it was before the mid-semester.
Right.
Now we can't do that.
So, sorry, just to add on one more
Yeah.
question. Just now when we were learning the one with the circle
Yeah,
characteristic.
yeah. Impedance relay.
Because we're looking at the line impedance, right?
Yeah.
And the line impedance is like almost all the time like inductive.
Yeah.
Then is that why we can?
If it is very good question. You should ask that during the class.
No, I just thought of it because I was like, oh, if it's line, then can't we just like, then it's kind of back to the directional in the first place, right?
Then characteristics looks like that,
Right, yeah.
right? So then, because this is the line impedance, right?
Yep.
So if it is not, it's like that,
Yep.
right? So now you have the directional, but the problem is that, say, typically this impedance, sometimes that you want to cover a little bit in the more towards the arc direction because of the arc resistance and all,
Oh, okay.
right? So, and also sometimes these lines have impedance like ZD equals, let's say, 5 ohms with 80 degrees. Got it? Not
Yep,
90,
yep.
right? So then, it's slightly slanted like that. Okay?
Yep.
And then, if you slanted it like that, then it crosses a little bit in this region as well. Right? It goes to this domain here.
Oh, okay. But no, most of the time then it should happen here, right?
Oh,
Because,
yeah.
like, this is like negative resistance, which is
This side is basically usually it won't happen in this region, because as you said,
okay.
you know, the impedance, let's say the fault impedance or impedance that you are measuring is lying somewhere here,
Right.
or if it is reverse conditions, then somewhere here.
Yeah.
Very rarely that you go into this region.
Right. Yeah. Understood. Yeah.
Right? It's a reverse resistance.
Right.
Right.
Okay. Okay.
So
Yeah.
that-
That makes sense.
Yeah, so that you are mostly in that region.
Right. Then would the capacitive part.
Capacitive, this is the fault.
Right.
Fault is not capacitive.
Okay. Yeah. It's,
Right?
it's
So
purely
if
line.
yeah, the load is here, that's fine.
Okay,
Right?
understood.
Problem is that if the load is very, very low, high load and capacitive, then it could come to here.
Okay.
Right? But that's why that, as I said, there is a technique which I will do in one example. Load encroachment.
And because you say like the shift when we shift the circle like mathematically.
Yeah.
Would that mean that essentially all these are done through numerical relay, like it's impossible for mechanical?
Mechanical, they can, because that,
mechanical.
yeah. So then they have more relay is basically this characteristics in when you go into the y, what is the s domain, like 1 upon r and 1 upon x domain.
Oh yeah,
Right?
okay.
It is a sort of a line. So what it does, because the same characteristics, you
Right.
can define it as a line, because
Oh,
you are
okay.
taking the 1 upon that,
Ah,
right? So,
okay, okay.
so that you basically invert the both axes.
Yeah.
Okay, so that it's mathematically what happens is that this becomes a line. That's why that Ohm came.
Okay,
Ohm is resistive,
Yeah, so the opposite.
opposite
yeah.
of it. So then once you introduce that, now you don't need this, because in the numerical relay you can quickly
Yeah,
introduce it,
I mean
right?
it's just coordinates, right? Basically just I add like a few numbers.
It's numbers, and then
Yeah.
it can identify what is the circle radius and everything, right?
Okay, yeah.
But
understood.
when it, as you said, when it goes to this one, the mechanical type or old types, then it's hard to go with the circle.
Yeah, well, now
Right?
I was just wondering like
Yeah.
how
So
are you
then
going to shift
they go with
coordinates?
this one, and then it is linear. Once it is linear, then you can work with a lot of mechanical systems.
Yeah, that makes sense. Yeah, if it's
Right?
linear, then
Linear
then
is much
mechanical
easier.
is achievable.
Achievable.
It's just a coordinate shift, like the
Yeah.
circle
No,
shift.
it's like this.
Yeah.
Like, you know, when you once you measure it, then you need to identify how to calculate, you know, 1 upon quantities, right? In the mechanical relay, you have to take the inverse of something.
Is that possible for like mechanical?
I think you can do it using the small, taking small relationships between certain things, right? Magnetic fields and electric field.
Okay, okay. Understood.
So it's
But the idea is that
yeah. So
Okay.
if you don't do it in that way, that linearly, then I don't think that there's a
right.
way to
Okay.
do it. Even
Right.
even books are not talking about it now, because
It's too old.
no, too old,
Yeah.
right? Yeah. So
Okay, thank you. Thanks
no
a lot.
worries. See ya.